Today is our last day of notes on section 9.4 polar coordinates. Tomorrow is going to be a review day, and then next week you will have a graded assignment on polar coordinates on Monday. So what we're going to look at today is converting from rectangular to polar form. And we did this only for the points that were on the axes yesterday. So we want to look at any other point. So if we are given rectangular form, we're given x and y coordinates. So rectangular form tells you go over x and then go up y to get to the point. This is the way we've graphed our whole lives until this week. So polar form, we want to give the radius and angle of that same point. So if I'm going to convert this to polar form, I need to connect the origin, which is our pole, to the point P. And I need to find the angle theta and the radius of that triangle. That radius is the hypotenuse of this right triangle that I now have. The x and y coordinates are the legs, the radius is the hypotenuse, and theta is this angle. And theta is always an acute angle, but depending on which quadrant we're in, we're going to use that to get the theta that is actually in the name. So if I look at this triangle, I can find r by using Pythagorean theorem. R squared equals x squared plus y squared. You would do x squared plus y squared, take the square root, and get the value of r. And again, when we go to polar coordinates, we're always going to make that r a positive radius. And we're going to name these angles between 0 and 2 pi radians. Or if we were going in degrees, we would go between 0 and 360. So we're going to go in the positive direction. Now, if I look at the triangle, I want to write an equation that involves theta. I know x and y, I know both the legs. So the tangent of theta is opposite over adjacent is y over x, which means I could solve that equation for theta. Theta would be the inverse tangent of y over x. That's the theta inside the triangle. You have to be careful if you're using this equation because theta will always be an angle between negative 90 and positive 90, between negative pi over 2 and positive pi over 2 if you use inverse tangent. That's because that is the range of the inverse tangent function. So we need to know the quadrant in order to find theta. If you're using this straight equation, you would then add pi to the answer for the inverse tangent in order to get the actual angle when the point was in quadrant 2 or quadrant 3. I'm going to show you a little bit simpler way to do this that doesn't involve the equation, but is more visual or geometric in approach. So here's my approach to doing these. I have the point 2, negative 2. I'm going to draw that point. 2, negative 2 means I go over 2 and then down 2. It's a point here where I have gone over 2 and down 2. I want to find the name for that point by finding r and theta. So I'm going to connect from the pole, from the origin, out to my point. When I look at this, I have a right triangle where the legs have the same absolute value. Again, yesterday we talked about 45, 45, 90 triangles. The legs are both x, and the hypotenuse is the leg times the square root of 2. If you see that these legs have the same absolute value of length, that must come from this isosceles right triangle. So if the legs are both 2, the hypotenuse would be the leg times the square root of 2, 2 times the square root of 2. And I want to name theta where theta is between 0 and 2 pi. So I want to name this angle going in this direction. This is a 45, 45, 90 triangle, so that's pi over 4. I'm 1 pi over 4 short of 2 pi, 1 pi over 4 short of a full revolution. So my radius is 2 root 2, and my angle is 1 pi short of 2 pi. So 8 pi over 4, take away 1 pi over 4, that angle is 7 pi over 4. If I was doing this in degrees, I would say I'm 45 degrees short of 360. 360 minus 45 is 315. In the second example, my x and y coordinate are -1 and -√3. So I'm going to draw a point that goes -1 and then goes down square root of 3. I'm just going to square root of 3 is like 1 point. So let's draw that again. My x and y axes, I'm going to go over 1 and then down square root of 3. Over 1, down square root of 3. And what I need to recognize is that 1 and square root of 3, anytime one of the legs is square root of 3 times as long as the other leg, that comes from a 30, 60, 90 triangle, where the shorter leg opposite the 60 is my x, opposite the 30 is my x, and opposite the bigger angle 60 is x root 3. So here, this is my shorter leg and longer leg of my 30, 60, 90. In other words, the angle in the center here has to be 60 degrees or pi over 3 radians. The shorter leg is x, the hypotenuse is 2x. So here, if the shorter leg is 1, the hypotenuse has to be 2. And our radius is always positive when we name these. So my radius is positive 2, and then I need to name that angle going around in the positive direction between 0 and 2 pi. This is pi, which is 3 pi over 3, and I've gone 1 pi over 3 past that, which is 4 pi over 3. So these are points that when I'm given rectangular coordinates, I can convert to polar coordinates in exact form because they're all points that I can represent as the sides of 30, 60, 90s, and 45, 45, 90 triangles. I'm going to do one more example where the point is not from a 30, 60, 90 or 45, 45, 90, and this is a problem that you would need a calculator for. I have the point 3, -4. So this is the point where I've gone over 3 and down 4. 1, 2, 3, 4. There we go. I've gone over 3 and down 4. If I wanted to put this point in polar coordinates, I would need to know the radius, which is the length of this hypotenuse, which this is a 3, 4, 5 right triangle. That would be my radius. And I would need to know the angle going around in this direction. I can find theta inside the triangle by saying the tangent of theta is -4 over 3. If you do that, and then you take the inverse tangent, you will get that the inverse tangent is that the angle is -53.13. Or if you used positive 4/3, you would get positive 53.13. What I have to realize is if I get this negative angle, that's how many degrees short of 360 I am. I'm going to do 360 minus 53.13 to get that this angle is 306.87 degrees. And if we were doing these problems, we would leave them in degrees. For your homework, you're going to focus on these problems where they come out exact, but I want to remind you that not every point can fit on a 30, 60, 90, or 45, 45, 90 triangle or as a multiple of one of those angles.